Okay, we're going to start a new unit today, which starts to really get into some important machine learning topics like overfitting, underfitting, bias variance trade-off. This is also where we will get into statistics and probability, so we will review that not today, but probably on Friday. So in the last lecture, where we learned about linear regression, we saw that one of the things we can do with linear regression is actually polynomial regression. So in polynomial modeling, we have, in this case, scalar features, meaning there's not multiple features we're using to predict the target, but just a single one, so little lowercase, not bold x. And the idea is rather than just using a linear model, which would be this, we add some additional terms that take x to successfully higher powers, all the way up to the dth power. And so this is called polynomial regression. We can use all the tools that we learned for multiple linear regression. Essentially, we just call this the first feature, we call this the second feature, all the way up to the dth feature, and then we just, with that new, larger, kind of expanded data set, we just do multiple linear regression, so we know exactly how to fit the beta coefficients. But the key question is that when we do this with data, we have to choose D. We have to make a choice of how complex our model is going to be. As D goes higher, we have more of these terms that we have to fit using the available data. And so that's the main question of this unit, is basically how do we choose D in a sensible way. And this problem is an example of model order selection. Model order meaning simple models to complex models. And what we're going to do in this unit is, rather than using a real-world data set, we are actually going to use a data set that we construct ourselves from synthetic data. And in particular, what we're going to do is we're going to generate this data set randomly, and we're going to, for the features, the examples of our single feature x, so for the xi, we are going to choose numbers randomly with a uniform distribution between -1 and 1. And so if you in my notes see these square brackets around two numbers with a comma, that denotes a closed interval. In this case, a closed interval from -1 to 1. And the way that we're going to generate the data in this case is we are going to generate the ith training target as some function of the ith training feature plus a noise variable that we're going to call epsilon I. And the function that we're going to use looks like this. So this is our polynomial model, but it's going to have a very particular order. It's going to have what we call D true as the order. For this data set, we're going to use D true equals 3. And there's going to be some true beta coefficients that we're going to use to generate our data. So that way we know exactly what the ideal betas are, and if we construct some betas using some method, we can compare them directly to the true ones, and we can ask how good are they. The noise epsilon is going to be generated using normal distributed or Gaussian. So this is normal or Gaussian, same thing. So this is the notation we're going to use in this course for that. This is normal Gaussian distributed and this is with a mean of 0 and a variance of sigma squared. We're going to talk about random variables pretty soon, but I believe you've all seen these in a prerequisite class, so you're just going to generate some random noise samples that are 0 mean, sigma squared variance, and sigma squared, the standard deviation of the noise is 0.4, so sigma squared is 0.4 squared. So the advantage, as I said, about using synthetic data is that we know the ground truth. This is really useful sometimes when you design a system. Before you try applying it to real data, you make your own data set that's synthetic, that you understand exactly how it behaves, and you basically develop your model with that synthetic data set. You learn about it, and then once you feel better, you start to involve real data. You can learn some more stuff with real data. But we're going to use synthetic data for all the demo examples in this unit. And here is an example of the data set from the demo code. So you can see what I'm showing you here is this is the feature value and the target value. A scatter plot are the blue dots, and you can see that the features are distributed uniformly between -1 and 1. And then the target value y is basically, this is the true model. This is our f of x. And then the deviation of the blue dots from the true model is due to that Gaussian noise. 0 mean, 0.4 standard deviation. Okay, so from this data, we ideally want to learn that red curve. The red curve is unknown to us. The red curve is unknown to the designer of the model. Of course, since we are generating it ourselves, we have that knowledge, but is the setup pretty clear? Any questions on setup? Okay, great. So we're going to first talk about what happens when we fit a model with the true model order. So we assume that a genie tells us that d equals 3, or we make a lucky guess that d equals 3. In the last unit, we learned about some different methods to actually do the computation of the betas in Python. One that we recommended was this scikit-learn linear model.linear regression. We could certainly use that. The way to use that is we have to construct a feature set with d different features where the jth feature is going to be the original scalar feature raised to the jth power. But we're actually going to do something slightly different. We're going to use NumPy's polynomial package, which is able to do that least squares fitting, but it's also able to do a whole bunch of other useful polynomial sorts of things. So that's what we're going to use in this unit. I'm not going to get into the details of the Python. You can see them here in the lecture slides. These snapshots are taken from the demo code. It's very straightforward. It's pretty easy to use. But in any case, once we do this least squares fitting with the provided data, we get that green curve. And you can see the true curve and the green curve are a really good match. They're not perfect, right? We don't expect them to be perfect because we don't have an infinite amount of data, only I think 70 samples, but I would say that's a pretty good fit, all things considered. So that's what we have. Least squares fit is very good. But if we would have used the wrong model order, things are not as good. So for example, if we would have used as our model d equals 1 to try to fit this data, as we know that is just simple linear regression. That means we're fitting the data with a line. And you can see that the line is this green line. And while it is the best fitting line to the data in the least square sense, it is sort of underfitting. It's not fitting well here. It's kind of below the data here. And in other places, it's above the data, and so on. And so you can see that the red, true model order is much better. On the other hand, we could have selected a model that's overly complex. So on the left, we call this underfitting. On the right, when we have a model that's more complex than the truth, then we get this squiggly green curve, and you can see that it's doing some kind of crazy stuff. It's really reacting to the very specific patterns contributed by the noise that was randomly generated in this data set, right? Because remember that the reason that these samples are up here and not on the red curve is because the noise that we added happened to be more positive than negative in this region, and happened to be more negative than positive over here, and so on. And so what's happening is that the prediction model, it doesn't know the difference between noise and the true model. It just has the data, and it ends up coming up with this green line as the best polynomial fit to the data with 15 power polynomial. So that's an example of overfitting. And this is another illustration. It's just kind of a stylized one, but here's a good fit to this data. You can see that the model is sort of going through the data, keeping the sort of overall trend without getting distracted by the very specific noise and characteristics of the exact samples. And in fact, it's possible to, if you have a powerful enough model, to go through all the data points perfectly. So from the perspective of least squares fitting, if you go through all the data points perfectly, you get zero fitting error. That seems like a great thing, right? So what's the problem with this in general? Let me ask, is Daniel Singer here? Yeah, so what do you think, why is this not a good thing to do in the bigger picture?
I guess it's a little too specific. It's not giving you general trends, and it's just going point to point because you're trying to use it to predict stuff. You can't really use it.
That's all true, but there's something else I'm looking for. Let me ask. Let's see, is Vedant Karthik here? No. Okay. What about William Huang? What about Joshua Joseph? Yeah. What do you think?
When you test this model against other data, it will be pretty off.
Exactly. Because this particular model is fit to some idiosyncrasies in our training data, some strange properties of the training data that are not going to hold true in the test data. So if the true model was something like here, the training data noise happened to be positive here, but the test data noise could be negative, and then you have a huge discrepancy. So that's really the issue, is that it's fitting in a way that's great for the training data, but could be especially terrible for other data that is generated from the same physical model or whatever the model is generated, but it's just a different kind of random sample from that model. So that's the issue that we're fighting here in overfitting. And of course, underfitting, the trouble is there's a true model that's more complicated than what we are assuming for our model, and so we're not going to be able to really capture the true model variations because our model is too simple. So what we want is we want something in between, like the kind of Goldilocks fairy tale. We want something that's not too undermodeled, not too overmodeled, but somewhere in between. Any questions on the general idea of underfitting and overfitting? Okay, good. So now we're going to start to think a little bit about how we actually do this. And we'll start with a really simple and kind of naive approach to thinking about how we might find the true model order or find a model order that works well. So one idea is select the model order that minimizes the training MSE. So to give you a little bit more detail, what I mean by this is you run a for loop, where in that for loop, you have a list of different possible model order hypotheses. So here we're starting at 1, 2, 3, 4, and so on, all the way up to, let's say, 14. So we have all these different possible Ds, and for each of those Ds, what we can do is we can compute the least squares coefficients. There will be D plus 1 of them. Then we can evaluate the predictions on the targets. And finally, we can evaluate what I'm going to call the sample training MSE if we assume a model order hypothesis of D. Okay. So let me just explain a little bit what I mean by this sample MSE. So we are going to get into statistics later in this unit, and we're going to distinguish the statistical MSE from the sample MSE, which is going to be kind of a fancy version of the difference between the statistical mean or expectation and the sample mean that we reviewed last unit. So statistical mean versus sample mean, two different things. So here, this is a sample quantity. As you can see, it's based on just the sample average of the squared difference between the true and predicted training targets. Okay, so that's what we mean by sample MSE train. So again, we run through a list of possible, hypothesized model orders. For each one, we compute the coefficients, we compute the predicted targets, and we measure how good that prediction was in terms of sample MSE. And what we're doing here is we're making a plot of the sample MSE versus the hypothesized model order. Okay, D. And you can see what happens when so remember, the true model order that we happen to know is 3. Okay, this algorithm doesn't know that, but 3 is the true one, and this is what happens at 3. Let me see, D true is 3. So you can see that when we underfit, we have very large error for D equals 1 and 2. Then once we select the true model order, we see a big fall off in the error. But if I select larger, more complex models in the truth, my training sample MSE keeps getting lower and lower. Right? So what does this tell you about this overall scheme that we're kind of proposing? Is this going to be a good thing to use or not a good thing to use? Not a good thing, right? Because this will always tell you to choose the largest D among your hypothesized values. It's going to basically just tell you to overfit. So this is not a good approach, but it is sort of like the first step on the way to thinking about how you automate model order selection from the data itself, because that's really all we have in practice. In many cases, we just have the data. There's no genie telling us what the right, properties of the physical model are. It's just we have to figure it out from the data. Okay, so this is a bad idea. So let me put a frowny face here. Any questions on this method? Yes.
So that was a way to determine order, just to look at the drop in error per jump in order.
It turns out it's not really a robust method. For this data set, it seems like it's kind of a good method, and it is like a heuristic that sometimes people will use, but we'll develop some more robust methods that are used much more often in machine learning. Okay, good question. Any other questions? Okay. All right, so let's try to understand a little bit more about what is going on with this overfitting problem. So really, when we're doing this model order selection, we can think of choosing the beta vector from a set of different possible beta vectors that have a certain structure. So, for example, if we hypothesize that D equals 1, then the beta vector has beta 0, which is our intercept term, beta 1 our slope term, and then everything else is 0. We don't allow, it's like we force all the possible larger beta coefficients to 0. But if we allow D equals 2, then we are fitting a beta 0, a beta 1, a beta 2, and then zeros, and so on. And if we do d equals 3, then we are allowing possibly non-zero beta 3, but forcing all the other coefficients to 0. And you can kind of see now the structure. So every time we increase the model order, what we're doing is we're kind of allowing a model that is more general and more capable than the previous model. In other words, like this model can do everything that this model can and more, because if it wants to mimic this model, it can do that just by setting beta 2 equals 0, but it can actually go beyond that and do more than setting beta 2 equals 0. So that's why it's more capable, it's more general, it can in some sense fit a larger range of problems, but that's not necessarily a good thing from the perspective of overfitting, but it helps us understand what's happening when we choose this model order. So as this model gets more capable, its ability to minimize or train MSE improves, right? Because it has like these extra knobs that can be turned. And so in some sense, that's why if you say your goal is to minimize training MSE, yes, this one will always do at least as good and usually better than this. And then this one will do at least as good, if not better, than this, and so on. And that explains why the training MSE keeps going down. When you ask it to minimize training MSE and you see how well did it do that, it's only going to get better. Is that idea kind of clear? Explaining where this overfitting is coming from? Okay, so if you think about this more, if you make D large enough, so if I make D, let's say equal to n minus 1, n is always the number of samples in our data set, what are the dimensions of this matrix A? Remember, how many rows does A have? N, right? A has n rows, and how many columns does it have? D plus 1, right? And so if D plus 1 is n, if D is n minus 1, D plus 1 is n, then the matrix is square, right? And if the matrix is square and the data is random enough, it turns out that that matrix is with high probability invertible. You can see that, okay, once I have an invertible matrix A, if you ask me to minimize this norm, I can do that perfectly. I can set it all the way to 0 just by choosing beta hat as A inverse Y. And if I do that, I will match Y perfectly. I will get 0 training MSE. And here's an example. My polynomial model is passing through all my training points perfectly, 0 training error. But as we know, that's not necessarily a good thing because look, it's doing something really crazy at this point here, making a really crazy prediction. Okay, so this is just sort of something to keep in mind. And as we said before, when D is large, Y hat is trying to fit the training noise, and that's the main intuition behind overfitting. It's like we want to fit the overall true model, but we don't want to fit the noise. That's the difficulty of the problem we're facing. Okay, so that's concepts behind overfitting. Any questions on overfitting? Is it sort of making sense, what's happening? Okay, great. So now we're going to get into the main method that is used in machine learning to get around this issue. And the main idea is that we're going to evaluate performance on test data that is independent of the training data. Maybe I could say evaluate model order selection performance. So when I want to choose my model order D, instead of looking at how well the model is doing on the training data, I look at how well it's doing on some set of test data that is generated independently of the training data. We'll get into more details of what we mean by independent. But the way this is done in practice, in the simplest case, is super simple. You imagine that you are given this one big data set, and you split it into 2 subsets. You partition it into 2, and you call those 2 subsets folds. You have your test fold and your training fold. So the training fold, you have to make a choice of how many samples to use for training and you use the remainder of the samples for test. That's a choice you have to make, but you can make a choice here. So for the training samples of quantity n train, you get these feature label pairs, and then the remaining samples, n total minus n train, that's n test. Those are what you use to evaluate your model order selection performance. Okay, so here's the revised approach, is again a for loop where you hypothesize a bunch of model orders. For each of those hypotheses, you fit your beta hat coefficients from the training data, because by definition, the training data is what's used to get your beta hat. But then you predict the test targets, not the training targets, but the test targets. And then you compute the test sample MSE. So here you're using the test data, not the training data. And the intuition, why this works, is because it's impossible to fit the noise in the test data if I have never seen that test data when I built my model, when I trained it. So it's sort of immune to that. And here is just an example of how this worked out in the demo. It's not perfect. So the training curve, the blue curve, is the one we saw before. But now we have a new curve, which is the green one. And you can see that it gets better, not necessarily monotonically, but overall it gets better around the true model order. And then it starts to get worse. And if we would have continued testing higher hypotheses, this would eventually have gone up. So did this work out perfectly? No, because if you look very closely at these 3 points here, this one at d equals 5 is actually the best one in terms of test MSE. And so that's what the model would have selected. And it's not ideal, but as you can see, it seems like it's a decent choice. It's certainly better than choosing 9, which is what we would have gotten if we would have used the training data. So we will eventually come up with an improvement on this technique, but this is sort of just our first cut at how you do what's called cross-validation. This whole procedure is called cross-validation, which basically means you use 2 different data sets, one to train, one to test. Okay. Not perfect, but a big improvement over what we did before. Any questions on this approach? Yes.
Does it mean we have more test data sets you will predict better?
Yeah, so we'll see that in general, as the number of test points increases, you'll get a more robust estimate of how your model performs on unseen data. But also, the more training points we have, our model also gets better. So we have this difficult situation of we want to maximize both the number of test and training samples, and we can't because it's a zero-sum game. I only have n total, and I have to split it up. So this is an issue we face. But yes, we would ideally like to have as much data as we can get. Okay. Any other questions? Okay. Great. So this is the simplest approach, often called a test-train split. But there's a more sophisticated approach, which aims to get around this idea, which I just said as an answer to this great question. We face a difficult trade-off in how much data we use for training versus test. We want to use a lot for training, but we also want to use a lot for test, and we can't do both. So as an improvement, we can do something that's more computationally intensive to sort of get around that test-train zero-sum game. And it goes like this. It's called k-fold cross-validation. And what we do is, number one, we take our data and we shuffle it. So let me explain why this is important. Some data sets come to you in a very organized way. So maybe I have a data set where I'm trying to recognize handwritten digits. And maybe like the first 100 samples are all digit 1. The next 100 samples are all digit 2, and so on. If I don't shuffle my data and I look at that first 100 samples and I design a predictor from that, and then I test it on later ones, it's a disaster because that predictor only learns how to deal with ones. And it's going to work terribly on all the other numbers, which it's never seen. So to get around this, we always want to shuffle our data as the first step. You just take your data, you randomly shuffle all the sample indices. So now, if I look at the first 100 or the second 100, statistically, they're all the same. Okay, so now I've shuffled my data, and what I do is I partition it into k folds of equal size. And what I do is I use the first k minus 1 for training, and that leaves me with one fold left, which I use for testing. So here's a visualization. So here's my training set. This is I equals, let's say, 1 to n. And this is shuffled. And so now that it's shuffled, I'm okay with using the first k minus 1 folds for training and the last one for test. And notice that in doing this, I can actually use, if I can make k relatively large, let's say I make k equals 10, I can use 90% of my data for training, which is good. I'm using most of my data for training. Now you might say, well, I'm only using 10% of my data for test, but that's where the next stage comes in. That's what we do in the first iteration. Use these for training, this for test. Next time, without any reshuffling or anything, we use these for training, and we use this for test. And we keep doing this until the kth iteration. In this picture, k equals 10. And so in doing this, I end up designing k different models. For each model, I end up evaluating its sample test MSE. And when I'm all done, I average these sample MSEs, and I get an overall test MSE for my data set. So now in doing this, you can see I'm able to use most of my data set for training, right? At the same time, I'm also able to use all of it eventually for testing. So I kind of get the advantage of both. So what's the catch? The catch is computation. I have to do my model design, my model fitting k times. In some cases, it's just too expensive. You might say, like, I can't even afford k equals 2. In other cases, if you have a small data set, you might go to an extreme. You might say, I'm going to do this to the extreme where my test fold contains one sample and my training contains n minus 1. And that is it has a specific name called leave one out cross-validation. Okay, so that's the maximally expensive model, but in some sense, like the most robust. You can use most for training. It's just you have to design a lot of models. Yes?
Is this, you're training 10 different models, or you're training one model with 10 different sets?
Well, so each time I have a different training data set, right? And so I'm going to get different beta coefficients. But what I'm doing, so actually I didn't describe the final thing, the final stage. So I'm doing all of this just to figure out the model order. Okay, so like I train a model based on this data, and then I compute the test MSE, and then I throw out the beta coefficients. Then I do it again, and then I throw out those beta coefficients. When I'm all done, and I can look at this, I can make a decision on the model order. And then, once I know that, I can use all my data for training if that's all I cared about. Now, often, the test data is not only for choosing the model order. Maybe you use it to figure out other things too. But if that's all you cared about, you could use your full data then for training. Okay, so that's k-fold cross-validation, and that's like one of the most important basic methods in machine learning. So what are your questions on this? Yes?
Why 10?
Oh, that's a great idea. So typically people use 5 or 10. There's been some statistical studies. There's papers written about this where they basically said that these are good values based on all these. They have a lot of arguments for why. At the end of the day, there's a trade-off between computation, like as k gets too large, it's a lot of computation. If k is too small, like, let's say if k equals 2, then what happens is you would use half your data for training and half for testing. But the problem is your training models, the ones you train to figure out your model or selection, are always only using half your data, so they're not going to behave like the true model, the final model that uses all the data. So there's going to be sort of a statistical mismatch there. So at the end of the day, some statisticians have analyzed this, and this is what's recommended in the textbooks. 5 or 10 is usually good numbers. Yes.
So in practice, when you're actually adjusting the weights to train a model, doesn't the training also kind of use the structure where you would subset out a bit of the data for like testing, like sanity check eval along the way with training?
Yeah, that's what I was saying, that you can use this, you can use these test quantities for more than model order selection. That might be one thing you're doing. You might actually have other tunable hyperparameters in your model that you need to choose. So you also use it for that. You might use it as a sanity check, like, is this thing working at all? So there's actually a lot you can do with that holdout data. Exactly. Yeah.
So for each of those iterations, you're also doing multiple trainings on each of the Ds, right?
Yeah, we'll get into that next. That's exactly right. So this is just like if I had, we haven't really gotten into how we do the model or selection. This is just like, how do I evaluate how good my model is at the moment? I want to use test data that's not training data, but I want to navigate this balance between how much training versus how much test. And this is a way to get really good trade-off at the expense of computation. Okay, any other questions? Okay, excellent. So now we'll get into how we do the model order. So really we need 2 for loops, 2 nested for loops. The outer loop iterates over the folds. So like that would be basically this loop. But then let's say for this particular fold of test data, now we have an inner loop that loops over the different model orders in our list of model orders we want to try. So for each pair of K and D, we would compute the sample MSE for that particular DK pair. And that gives us, a set of these, but actually one for every D as well. So it's like we have a whole matrix of sample MSEs. And then we can average over the Ks. So here's the sample MSE for the DK pairs. Now I average over the Ks. Gives me an averaged, that's what the overline is, average sample MSE for hypothesis choice D. Right, so that's, if we choose model order D, this is a sample MSE we expect to get. So now we can make a plot similar to this, where we have a bunch of these sample MSEs versus D, and now we can choose the smallest one. We can choose D as the one that minimizes that. Choose D, giving the smallest sample MSE bar. And the code, this is how you would code it manually. So here's the outer loop, and here is the inner loop where we go over D. And if you think about it, actually, if you really wanted to just code this completely from scratch yourself, you might realize that one of the tricky things that you have to do is you have to keep track of which index sets we use for training and for test at each one of these iterations. And it can be a little bit of a pain. And so that part is automated by scikit-learn. It gives you this k-fold split method that basically generates the training and test index sets every time you go through this loop. And then you can just easily pull out like the training features and labels and the test features and labels. It's easy to get them. So scikit-learn helps you with this. Now, there actually is even more slick ways you can use scikit-learn where you can do all this in one line. But I think it's important to show you guys what's actually happening under the hood. And this is what's really happening. There's these 2 for loops going through, trying every combination of fold and model order D. And then it's going to be averaging across the folds and then choosing the one which minimizes the model order D. Okay. Any questions? Is this making sense? Okay. Everybody good on this? Okay, great. So now we want to still improve this method further. And the key idea is that when we do this averaging over folds to get this sample mean, this is imperfect, especially when k is a small number. And I think you guys all have that same intuition. If I say I want to average a bunch of data, but I only have like a few points, like 5 or 10 points, you're going to be like, okay, but your average is not going to be super accurate. The fewer points you have, the less you should trust that average. Just like intuitively, if I want to, let's say someone is flipping a coin and they're telling me that this coin actually is biased towards heads versus tails, and they want to convince me of this, they're going to have to do a lot of flipping before I'm going to believe them. If they flip it twice and say, look, it showed up heads both times, it's biased towards heads, you'd be like, no, you didn't have enough examples, didn't have enough data to really convince me. So this is the same issue here. The number of folds we use in practice is not that many. And so the estimate of the sample MSE we get is not really perfect. And okay, what do we mean by perfect? Well, there's this true statistical MSE, which we'll get into the next lecture. This is, you could say it's an estimate of that, it's an imperfect estimate of that. So this is a very common thing in statistics to come up with some sort of estimates based on averages, and this is a very, very general thing. Maybe you want to answer the question, what is the starting salary of a graduate of ECE? And you want to get like the average, but then you also want to get confidence bounds. Like, if I only did this with like 5 employers, 5 numbers, and I got some number, I might not want to trust it. So I might want to say, here's some confidence bounds. It should be within, above this level and below that level, I believe that's within that interval. And the main way to do confidence bounds in statistics is something called the standard error. And this is probably something you guys have all seen at some point, but it looks like this. The standard error is defined as this sample standard deviation that we're going to compute, and we're going to compute it based on the sample MSEs that we collected. And we're going to divide that by the square root of the number of terms in the average k. So this is the key. You don't just, if we have like, if I give you 10 numbers and I say, what are the confidence bounds? You might first compute the standard deviation of those 10 numbers, but then the next step is you divide that standard deviation by square root of 10, and that's what gives you the confidence bound. So this is this divide by square root of k. So right now we are using this for model order selection, but I want to emphasize this is much more general than model order selection. This applies to any average-based estimate of any quantity, inside or outside of machine learning. So often, like on homework or test, I'll ask you a question about computing standard error for this quantity, and if you're like, well, that's not model order selection, I don't know what to do. My point is that it's always the same. No matter what it is you're trying to estimate, standard error is always defined the same way. You have a list of k numbers, you use them to compute the standard deviation, and then you divide by square root of k. Okay, so how do we compute the standard deviation? That's what's in the next step here. So here we have something you would recognize as the sample variance. So here we have this minus its sample mean squared and averaged. But what you'll notice is a little different than the stuff we saw in the last unit is that when computing the average, we are not dividing by k, but dividing by k minus 1. And this is something that is more useful as k gets smaller. If k is very large, like hundreds, thousands, or higher, there's very little difference in k and k minus 1. It's not going to have any effect at all. But once k is small, like let's say k is 3, there's a big difference between 1/3 and 1/2, right? So this is important when k is small. And what this does is it removes the bias in this variance estimate. We're going to get into bias in just a couple lectures, but this is what it's doing. It's giving us an unbiased estimate of the variance, and then we're taking this square root to get the standard deviation. Okay. So this is another sample statistic. It's just like we have a list of numbers. We can compute the sample mean. We can compute the sample variance. And so this is a sample standard deviation. This itself is imperfect, but that's just all we have to go on. Okay, so this is for this same example here. We're showing the model order, and the solid line is the sample MSE of the test data. And then you can see these are the confidence, this is the confidence interval that we are computing. And the size of the interval changes as you go, as D. So it starts out big, and as, in this case, as the model order is increasing, it gets a little smaller. So there is a very precise statistical meaning for, why are we building it this way, how to interpret this. We're going to get into that. But for now, we can just think about it as like, these are some reasonable values where you can say with pretty high probability, the truth should be somewhere inside that confidence interval. It's in there somewhere. We don't know where, but it should be in there. It's probably not over here, over here. As k increases, the size of these shrinks, and we can trust the average more and more. Okay. All right. Okay. Is this idea kind of clear? The standard error? Okay. And like I said, this is something you can use anytime you're doing any kind of averaging based on data. This idea applies. So in terms of the Python implementation, I just want to point out one thing. When you do the NumPy standard deviation command, you can specify something called the delta degree of freedom, DDOF, and that number is exactly this value 1. So in other words, if you want to put in a 1 here, then you set DDOF to 1. If for some reason you wanted -2, you set DDOF equal to 2 here. If you wanted to force this to be 0, then you could set DDOF equals 0. However, the default is DDOF equals 0, so if that's what you want, you just don't even have to specify DDOF. It just gives you this by default. Okay. But otherwise, I think the code is pretty straightforward. When in NumPy, when you take the mean of a matrix valued quantity, you have to say which axis are you taking the mean over the rows or the columns? So that's what this axis tells you, and so on. But otherwise, the code is very straightforward. So that's the idea of how we can compute confidence intervals to give us a sense of how much to believe these cross-validation values that we're computing using K-fold. Okay. Any questions on that concept? Okay. And then we can actually use these for a new method. And because it turns out that if you look at what happens by simply choosing the D that minimizes sample MSE, you'll see that it tends to overfit the true model order. So I shouldn't say sometimes, I would say usually overfits the true model order. And so to get around that, we're going to use an improved technique called the one standard error rule. And basically it says, use the simplest model that gives performance within one standard error of the minimizing model. And you guys have probably heard of Occam's razor as an idea. If you're given multiple explanations of something, the simplest one is usually the best. The same idea here. If there are a bunch of different model orders, that are giving me pretty much the same sample MSE, choose the simplest model among those. And in this case, the simplest model would be 3, not 4, 5, 6, or 7. And so, as you can see, now this is not guaranteed to always work, but in this case, it does actually give us the true model order of 3. So that's the overall idea behind one standard error rule. Is similar to Occam's razor. Simplest explanation is the best. The simplest among like similar explanations that all kind of explain the thing. And basically you could say all these model orders seem to explain the data equally well, so I'm just going to choose the simplest one. Okay, I can focus into the detailed procedure in just a second, but any questions on the overall idea here? Overall idea is pretty clear? Okay, so this is the actual like algorithm, you could say. First step is you find what we can call the minimizing model, d-min. So this is you compute versus d, those sample means of the sample MSEs, and you find the one that is the lowest. So in this particular example, it's hard to tell, but this is actually d-min with 7. That value was where the blue line is lowest. Okay, then you set what I'm going to call the sample MSE target as the sample MSE at d-min plus 1 standard error. So in other words, I look at the error bar there, and at the top of the error bar, I can basically draw this dashed line at what I call the target. This is the sample MSE target. So that's that orange level. And then finally, choose the smallest d such that the sample MSE at d is less than or equal to the sample MSE target. So I look at all these different selections. I say, of all the ones that are under the orange dashed line, well, that reduces us to these. Which is the simplest? Well, this is the simplest one that still is under the orange dashed line. D equals 3. So that is going to be the what we can call like the DOSE, D1 standard error is 3. Okay, so is that overall idea, one standard error rule, pretty easy? You'll have some examples of this on the homework. Later in the course, when we talk about other things, and we're also doing other forms of model order selection, sometimes the parameter that we're tweaking to get different model orders actually increases as the models get simpler. So in that case, you're going to be moving to the right. You're going to be sweeping some parameter and looking at the rightmost value because that's the simplest model. So just keep in mind, like when you do this, what is the simplest model? That's how this works. Simplest model that explains the data equally well as all other models. Okay. Great. Any questions on this? Okay. And one very last thing to point out is that sometimes we talked about splitting our data into 2 pieces, training and test, but actually sometimes people split it into 3, what they might call training, test, and validation data. So let's just be clear about what we're going to do with these different splits. So the training data is the one we always use to train the model parameters. In this case, it's like fitting our beta vector. The test data is the data we use to tune model hyperparameters. So we have parameters and we have hyperparameters. These are other design variables that are at a higher level than our basic parameters. So for example, model order. But these are both design parameters, so design. Now, you still might want to say, well, okay, I've done all this design. How good is my design? To figure that out, you have to have data that was never used for design. So you have a third set of data, your validation data, that you did not use for training and you did not use for test. You held that out to give you, a more accurate idea of how both of these things are working together. So training, test, validation. Now, the other complicating thing is that there's no clear definition for test and validation. Some people call the data used for the hyperparameters, they call that validation, and then they call the other data test. Like half the people say it one way, half the other way. So just keep in mind that test and validation, you have to figure out from a given source what they're talking about, but it's one of these two things. And then training data is always the same. That always means the same thing. Okay, so, all right, any last questions? Okay, if not, we'll see you guys Friday, and have a good one. Stay warm.